Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to discuss vector addition. So in this topic, we will describe the operation of vector addition. We will first look at real vector addition and then complex vector addition. We will discuss some of the properties thereof. Given two vectors in r to the n, we can add the corresponding entries. This is usually written as the vector u plus the vector v, and both must have the same dimension. So for example, if u is equal to the vector seen here and v is the other vector, then to calculate the sum of these two vectors, we just add the corresponding entries. So 2.7 plus 1.2 is 3.9. Looking at the fourth entry, 2.8 plus 0.8 is 3.6. You can compare and see that the rest of the entries also correspond to the sum of the corresponding entries. Now we may just write down the sum of two vectors explicitly without referring to any variables. In this case, we're adding two three-dimensional vectors. Alternatively, if we do not know what the vectors are, so here we have two arbitrary six-dimensional vectors, or vectors in r to the 6, then we could just represent the entries as the corresponding sums of the entries in u and v. Now, note that if you have a vector in r to the 4 and you add to that the 0 vector in r to the 4, then the sum of those two is just the vector v itself. Similarly, note that if you add a vector to itself, you just get twice each entry, which is also equal to the scalar multiple of v by 2. Also, here we have a vector in r to the 5. Notice that if I multiply that vector by -1 and add that resulting product to v, notice that the result is the 0 vector. Okay. Now, also note that if I add two vectors, so for example, here I'm adding two vectors to get the vector in the center, notice that that is the exact same vector if I add the vectors in the other order. So this suggests that vector addition is commutative. U plus v equals v plus u. Incidentally, vector addition is also associative. It doesn't matter what order you add u plus v plus a third vector w. Now, let's look at a geometric interpretation. If we have two vectors in R2, that is, two vectors in the plane, if we interpret these vectors as arrows coming from the origin, then the sum of these two vectors is equivalent to placing the base of one vector at the head of the other. So one possibility is to add v onto u. So here we see u plus v. Alternatively, we see that this is the same result if we were to add v plus u. The same goes in 3 dimensions. Here we have two vectors in R3, one, the blue one to the left below the xy plane, the red one to the right above the xy plane, and if we add these two together, we get this vector here. And this would be the exact same vector we got if we added the red vector onto the blue vector. Now, given two vectors in c to the n, then we can add them in a similar manner. For example, if I have these two vectors in c to the 5, then I can add the corresponding 5 entries in each of the vectors to get the result u plus v. So, for example, looking at the fourth entry, 1.9 minus 3.1j plus 0.8 minus 8.2j is equal to 2.7 minus 11.3j. Notice that if v is a vector in c to the n, then it should be clear that the following are still true. First, the 0 vector in c to the n plus v will leave v unchanged. And similarly, multiplying all the entries in the vector v by -1 and then adding that to v will result in the 0 vector. We also expect that for complex vector addition, u plus v is equal to v plus u. That is, it should still be commutative, and we do expect it also to be associative. That is, it doesn't matter which order you add three vectors in. Now, note that adding two n-dimensional vectors results in an n-dimensional vector. We are always going to be dealing exclusively with either real vectors or exclusively with complex vectors. There's no point in asking what happens if you add a real vector onto a complex vector. It's like saying, what happens if I start with 5 cups of water and then someone gives you 1 plus 2j more cups? Well, you don't deal with complex numbers to describe cups of water. So again, it makes no sense to have 2j cups of water. At least I've never had imaginary water in my life. Now, similarly, we can also only add vectors of the same dimension. That is, if they have the same number of entries in them. Like adding a 1,000-dimensional vector onto a 2-dimensional vector is completely meaningless. Now, it may be possible to interpret a 2-dimensional vector as a 3-dimensional vector, and then add that 3-dimensional vector onto another 3-dimensional vector, but that requires interpretation. We never will simply arbitrarily add a 2D vector onto a 3D vector. So, following this topic, you now understand the concept of vector addition. You've seen examples in both real and complex numbers. You've been exposed to some of the properties with vector addition, especially related to the 0 vector, and we looked at some properties and made some observations. Here's the references, acknowledgements, the colophon, and a disclaimer. Cheers!